Alright, today we're going to look at two things. We're going to look at, first, how to find vertical asymptotes. Now, what is a vertical asymptote? Well, look at this graph here. You see how, there seems to be some sort of imaginary line that this graph is trying to avoid, right? That's why the left side, as we approach 0, the graph goes up to infinity. And from the right side, as we're approaching 0, we seem to be heading down towards negative infinity, right? So what's going on here? What's happening? What is kind of like deflecting these two sides of the graph? Well, this is our vertical asymptote. At x equals 0, we have this like imaginary line, right? And I'm going to make this dotted in pink. We have this imaginary line that our graph is avoiding, right? So that's what's going on. There's a vertical asymptote. And you might also realize that we have something else going on horizontally, but that's for a different video, right? So how do we find these things, right? How can we look at a function of x and say, hey, there's going to be a vertical asymptote at this point? Well, that's what we're going to figure out how to do today. So let us look at this equation that I have here for us. F of x is equal to x squared over x squared minus 16. Now, the first step to finding these vertical asymptotes is to factor the numerator and denominator of our function, right? So we're going to rewrite f of x. Now, we are not going to factor our numerator because the factors of x squared are just x times itself. That seems a little redundant, so we can keep x squared how it is. However, we are going to change our denominator, right? We're going to factor x squared minus 16, and this, when we factor it, becomes x minus 4 times x plus 4, and if we multiply these two factors together, we'll get x squared minus 16 again. So these are our factors. Now, what's the next step? Well, you may remember we can never divide something by 0, and that's where we're going to have these vertical asymptotes occurring whenever there's some point x where we're trying to divide our function by 0, and we can't do that, right? So we want to find at what points will our denominator be equal to 0, right? So we have x minus 4, we'll take that one factor, x minus 4, and set that equal to 0. And we have our other factor, x plus 4, and set that equal to 0. And we're going to solve for x, right? And this is very simple. We know that this will be when x is equal to 4 and when x is equal to negative 4. So we have found that if we set x to 4 or negative 4, our denominator will become 0, and that is where we're going to have our vertical asymptotes. Anywhere our factors will cause the denominator to equal 0. So at x equals 4 and x equals negative 4, right? And I encourage you, if you have a calculator, if you're taking a calculus class and you have a TI-89 Texas Instruments calculator, graph this function and look at how the graph looks, and you'll be able to see those vertical asymptotes at x equals 4 and x equals negative 4. Now, so that was pretty simple, right? But now we're going to look at the second thing, which are removable discontinuities. And we've seen these in previous videos, right? Say we have some linear function like this, and then we get to a point, I don't know, we'll call it point n. We get to point n. Oh, okay, so we get to point n. Sorry about that. And there's some hole right here, right? What's going on here? Now, this won't really be, since we have a linear function here, this might be written out in a piecewise function where we'll say f of x is equal to blah, 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 except at n, But let's look at somewhere where we can actually find this by looking at a function where we can find these little holes where the function is undefined, right? How are we going to do that? Okay. We are going to look at this new function. F of x is equal to x squared minus 2x minus 8 over x squared minus 16. And we are going to factor this just like we did with the previous function, right? So f of x. This time we can actually factor our numerator, right? And when we factor x squared minus 2x minus 8, this is going to become, let's see, this is x minus 4 times x plus 2. Those are the factors, yeah. When we multiply these back together, we'll get our original. And then we know the factors of our denominator. We know that, because we just did this, we know that it's x minus 4 and x plus 4. And would you look at that? Would you look at that? We have the same factor in our numerator and our denominator, right? We have an x minus 4 in both those. Isn't that funny how that worked out? Well, this is something that we're going to look out for too, right? Because if we have this discontinuity, remember, we defined that at x, when x is equal to 4, our denominator is going to be equal to 0, right? And our function is not going to be defined there. It's discontinuous. However, since we have the same factor, x minus 4, in our numerator, we can kind of remove this discontinuity, right? They cancel each other out. And instead of having an asymptote at that point, we'll have just that little hole in the graph, which is why we call it a removable discontinuity, because we can technically remove it from the function, right? Little play on words. So this is how we find removable discontinuities. We factor our numerator and our denominator, and if there's a common factor, such as x minus 4, well then we take that like we did before, so x minus 4, set it equal to 0, solve for x, and we'll find that there is a little hole in our graph at x equals 4, and then we still have this x plus 4 in our denominator, which we can set equal to 0, solve for x is equal to negative 4, and we still have a vertical asymptote there. So like I said with the last function, I recommend if you have a graphing calculator, or if you know somewhere free online to do this, plug this function in and see how it differs from the previous function. You'll see that we still have that asymptote at x equals negative 4, but there won't be one at x equals positive 4 this time. Instead, there will just be a hole, and the function will be undefined at that point. So if you have made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.